So I explained yesterday that if we have a germ at the origin of Cn, here it's important that coordinates are fixed. Then there is a combinatorial object associated to it, which is called its local tropicalization, and which is the support of a fan. The fan is not canonical, so one can play with different fans with the same support. And when one has that fan, one can take the associated toric birational morphism with target Cn. That is not a modification, because that fan, its support is not the cone of Cn, but it has a property that it will be proper in restriction to the strict transform of Y. So if we are interested only in Y, it does exactly the job. So Y has the preferred families of fans with which to be modified. And what we hope is that to be able to resolve in this way. And that is the nicest situation, which is called Newton non-degenerate. Why Newton? This makes reference to the Newton polyhedra and the two foundational papers about this, about Newton non-degeneracy, and about the associated modifications, toric modifications, were published in 1976 by Kushnirenko and Varchenko. In the first one by Kushnirenko, Polyèdre de Newton et Nombre de Milnor, he proved a formula of the Milnor number of a Newton non-degenerate hypersurface in terms of the corresponding Newton polyhedron. And in the second one, the zeta function, which is a richer invariant, was computed using an associated toric resolution. Toric, in that context, he needed normal crossings divisor. So in fact, he subdivided the corresponding fan till all the cones were regular. So this is the explanation of the name, why Newton inside this. And a little later, in 1977, Khovansky extended the notion to singularities which were complete intersections. So you have to know that this paper is an English version of a Russian original, and the translation was very bad. So in particular, in the title you see Newton polyhedra and toroidal varieties. The correct translation is toric varieties. Wherever you see toroidal, here you have to read toric. And also Khovansky, I discussed with him this topic, and he was very annoyed. He said they really very badly translated my paper. And in particular, you see here the definition of non-singularity can be, no, not non-singularity. Here it's Newton non-degeneracy. And you have many problems like this. So if you have difficulties in understanding it, just know that it's not your fault. That you have to change each word till you arrive at something understandable. So in any case, here he extended this to a collection of series F1, Fk. And he precised the following. We note that the subject of Newton polyhedra began precisely from local problems, from the rich empirical material and conjectures of Arnold and the first results of Kushnirenko. So this was his conscience in the mid-70s. But in fact, somebody nearly completely unknown nowadays by the singularists already imagined this, to do toric modifications in order to resolve singularities, much before toric geometry existed. So I think it was in a context where nobody could have in mind a context to see the value of what that person did. That person was named Gustave Dumas, and he published two compte rendu notes in 1911 and 1912. Here is the beginning of the first one, on the resolution of surface singularities. So let f of something equal, there is a misprint here, the exponent 2 should be alpha. So the equation of an element of analytic surface. So here element could be interpreted as a germ in the neighborhood of the point xi equals 0 assumed singular. So you have to know that this is the year when Hausdorff published his Mengenlehre. So when you read here neighborhood, you do not have to think that there is a topological theory in which this has a precise meaning. We are still, as in the 19th century, where neighborhood is something you imagine you are in that space and you go nearer and nearer. So the term neighborhood came from that intuition, and then it got a precise meaning in a precise theory. But here we are not in a precise theory, things are still intuitive. So the object of this note is to show how we can, in this case, represent this element. So to represent this element is to resolve the singularity is a way of representing it. The singularity is something where we do not understand because a lot of structure is crushed there and the representation opens it. So how to represent the element? A polyhedral convex surface which plays the role of the Newton polygons in resolution of singularities of analytic plane curves is at the basis of the theory. So if you see how he expresses himself, you will see that for him, Newton polygon is not what I showed you. I showed you a two-dimensional convex polygon. For him, it is a boundary. So the polygon is really like a triangle for children, which is a union of segments. So here he looks in space as an analog, the boundary of a Newton polyhedron, which is a polyhedral surface. So after this first note where he explained in general what has to be done, in the second note, he showed that on a concrete example of the singularity defined by this equation here. So today, he says, I would like, by resolving completely the singularity of this surface, to show you the method. Here, he explains that the polyhedron has only one face, which is triangular, and whose edges are the edges 1, 2, 3. And he says to each edge, one associates a substitution which is expressed like this. So you see how toric geometry was present before it was born consciously in the 70s. Well, each time you see somewhere monomial changes of variables, you have to know that toric geometry is underlying things. So in this way, you can discover it even in Newton. And I think it's a wonderful adventure to go and find toric geometry in the last 400 years. You find it at many places. And here you see you have to know that in order to recognize it, you have to look for monomial changes of variables. And here he explains how one does compute the exponents starting from the exponents here. So you see that it is indeed singularity theory which again leads to a problem in which Newton polyhedra appear as an important tool. Sorry? Well, you find, I found them also in Newton, yes. Yeah. Because in fact, it's basic. You have something complicated, and the philosophy of changes of variables is you try to change variables such that something gets simplified. And people tried everything. And sometimes they saw, look, only this works. But it was in a realm which was not structured, in which you can try anything with sine and logarithms and absolutely anything. As we teach in first year of university, we tell them, let's do a change of variables. So, what is important here is to speak a little more about the way to arrive at local tropicalization when one has equations. Because I told you that we start from a precise system of equations defining splice-type singularities, and therefore we want to be able to compute local tropicalization for it. The two viewpoints I explained you before in terms of arcs or of toric geometry were theoretical. They help to understand what it means to take local tropicalization, but not how to compute it. The basis of computing local tropicalizations for defining series is to fix a weight vector, which means that each variable has a positive weight, and then to look at the part of a given series of smallest degree with respect to that weight vector, which is called the initial form with respect to W of the series F. And if we have an ideal, then simply we have to take the initial form of each element of the ideal and to look at the corresponding ideal, the initial ideal with respect to W. So here, computationally, the main problem is the same as one which leads to the theory of Gröbner bases, is that if you have a generating set of an ideal, the initial ideal is in general not generated by those initial forms. And you need to work hard to find another system when it works. But there are some situations which are especially nice because from the beginning it works. And that splice type singularities are especially nice, in fact. But all the time, the main problem one has in front of the eyes when one has precise equations is this one. When passing to initial forms, in general, we do not get the whole initial ideal. So, now what is a precise definition of Newton non-degeneracy? For us, we ask first that our set of functions be a regular sequence, which means that each function drops the dimension by 1. And now we say that it is a Newton non-degenerate complete intersection, which it follows, in fact, Khovansky's definition, except that Khovansky did not ask the first one about regularity, is that for any positive weight vector, if we look at the initial forms with respect to W of those functions, and now we look at the hypersurfaces defined by them in the complex torus, C star to the n, in the neighborhood of the intersection, we should see a normal crossings divisor. So we look where they intersect, and there, in the near that intersection, we should see a normal crossings divisor. So what can happen is that for some weight vectors, we don't have intersection. Those don't intersect in the torus. So what is interesting to check is only in which case that intersection is non-empty. So we get a preferred collection of weight vectors. And it turns out that, again, if you take the rays on them, their union, and you close, you get the local tropicalization. So this is a third way of viewing local tropicalization by looking at which weight vectors really give us an intersection of the hypersurface defined by initial forms. It's important to know that perhaps all singularities are Newton non-degenerate. And this is one of the important dreams of Bernard Tessier. He asked this repeatedly in various variants, sometimes related with some fixed valuations, otherwise not, like here. He asks the following. So first, he says an algebraic or formal subscheme of an affine space is non-degenerate at a point if there exist local coordinates there such that there is a proper birational map, toric map, here, in those coordinates, leading to a non-singular space, and such that the strict transform of the germ is non-singular and transversal to the exceptional divisor. So meaning, non-degeneracy means exactly that one can resolve the singularities in an embedded way by a toric morphism in the ambient coordinates. And what he asked is this question: given a reduced and equidimensional algebraic or formal space on an algebraically closed field K, and for him it's very important to include positive characteristics, is it true that for every point of X, there is a local formal embedding into an affine space such that X is non-degenerate? Which means are germs of analytic spaces or formal spaces or any kind of category, similar category, are such germs Newton non-degenerate after re-embedding conveniently in some smooth maze? And the subsequent question is, a subsequent problem is to give a geometric interpretation of the systems of coordinates in which an embedded toric resolution for X exists. So this is a very broad program in which everybody can see another way of attacking this. So the second problem seems very interesting to me because it's not one Newton non-degenerate presentation which will work for all the problems. Perhaps for other problems one has to re-embed differently. So even if, and there is a general positive answer, that one can do this re-embedding by a theorem of Tevelev, but it's a theoretical one for concrete singularities. If you want to see the equations of the re-embedding, there is still a lot to be done and to be understood about such embeddings.
Tevelev is in characteristic 0.
In characteristic 0, thank you. So this is still much open, and in fact, even if you hear, now it's known, if you go and you look detailedly at the question, you will see that even if something will be closed, a lot will remain open, like in topology. So let us see now. I said that once we have local tropicalization, we want to modify our germ using a fan which supports the local tropicalization, but not any fan. In fact, we have to care about a special property. Once we have a fan, we will look at the weight vectors moving in the relative interior of a cone. And what we want there is that the corresponding initial ideals be constant. And such a fan always exists. And we call this a standard tropicalizing fan. Why did we choose this name? Because the way to prove that it exists uses standard bases. So here standard makes reference to standard bases, which are a local analog of Gröbner bases. And so what is important for us is this proposition, which says that if we have a Newton non-degenerate germ and we fix a standard tropicalizing fan of it, and now we look at the strict transform under the associated toric morphism, then this strict transform is transversal to the toric boundary of the total toric space. So we have the transversality about which Tessier was speaking in his question. But there is here an important point of difference. Here we do not ask regularity. So if you are in a toric variety which is possibly singular, you have to give a meaning to transversality. So that's why I show you the next slide in which I explain this. Imagine that you have something more general than toric. We are in a toroidal variety. A toroidal variety is like a toric one. A toric one is not simply an ambient variety, but it has a fixed divisor, the complement of the dense torus, which we call D calligraphic of W, and toroidal is the same, but in the analytical category. And simply we ask that in the neighborhood of every point, the pair be analytically isomorphic to a toric germ. So this is unavoidable, even in toric geometry, if we look at these things, at subvarieties which are not toric. Because when you look at strict transforms of Newton non-degenerate germs, what you will get are precisely toroidal ones. In which way? So first, fix a toroidal variety and look at the subvariety V. We call it boundary transversal if the two conditions are satisfied. First of all, the toroidal variety, we have to stratify it in the same way as a toric variety is stratified into orbits. This means simply we said that locally it is toric. You take the toric stratification, and now you glue all of things, and everything glues correctly. And in this way, you get the toroidal strata, which are smooth. So now we ask that the intersection of V with a stratum be an equidimensional complex manifold. And this intersection is to be interpreted scheme theoretically. So indeed, you should not have there multiplicities. So here it's really manifold, so smooth and reduced. And second, a condition of dimension, that the dimension be as expected. So you look first at the codimension of the stratum in the ambient manifold, and it should be the same as the codimension of the intersection of V with the stratum inside V. So if you look at the usual transversality, you can see that it can be characterized in this way inside the manifold. So this is a way of extending it to toroidal contexts. And what is said here at the end is that our main example in this context of boundary transversal subvarieties are strict transforms of Newton non-degenerate germs by toric birational morphisms defined by standard tropicalizing fans. So the good context in which local tropicalization helps to arrive to a setting where then you can apply log geometry is a Newton non-degenerate one. And what is good is that after the modification, we have boundary transversality. And then if you intersect the strict transform with a toroidal strata, you get an induced toroidal structure on the strict transform. Sorry? Newton non-degenerate. This is exactly Newton non-degeneracy. Here it's not simplicial. Here you can have any cones, not necessarily simplicial, because you are happy if you are happy in the toroidal context. Like in the talk of Autumn yesterday, it was the same. He explained what is common with here, that if you start from concrete equations, is much more work if you want to regularly subdivide. If you take the cones which are given by the equations, you do not have in general regularity, but what you have is toroidal. So that's why we prefer to say, let's keep it, because log geometry explains us that we can be perfectly happy even there. So then comes exactly this question, why not to work only with normal crossings divisors? And we see several reasons in this context. First, what I just said, that the most economical standard tropicalizing fans, those with the least number of cones, and those which are directly related with defining equations, are not necessarily regular, which means that the associated toric varieties are not necessarily smooth. Second, any fan has regular subdivisions. So if we want to go to regular subdivisions, we can. But concretely, there is work to get them, and they are non-canonical, except in dimension 2. And third, precisely this, that logarithmic geometry works very well in the toroidal context. So in fact, if what we want is to understand tubular neighborhoods functorially using log structures, then we do not need to bother about regular subdivisions. This does not mean that one does not need to bother about them in other problems. But here, we could avoid this. So now I will go rapidly on this, as I teach to my students when I teach them to write something and also give oral talks. An oral presentation has an aim to push people to read what is written. So if you don't succeed to give them some need of that, no, it is meaningful. So I will jump. People who are interested, I present here a last viewpoint using evaluations on local tropicalization. The beamer will be available immediately after my talk, so you can go and see that. And why do I speak about this? Because Dmitry, Stepanov, and myself, when we wrote our basic paper on local tropicalization, we wanted to have a very general notion which applies both to formal germs, so to singularity theory, and which contains the existing global tropicalizations. We wanted also to have a tool like commutative algebra, which applies both to algebraic geometry and number theory. And in number theory, we have rings which do not contain fields. So we do not have to assume that we work with algebras over fields. And if you see the viewpoints I presented to you before, the first three work with something over C, or over a field. Power series with coefficients in a field, or polynomials with coefficients in a field. So when we wrote that paper, we wanted only to have rings. So this is another level of generality. And what we found, which allows to have factoriality and also to cover local and global context, is that the easiest definition is that which takes the valuative viewpoint. And that makes that paper difficult to read if you want to discover this domain. And that's why we accepted the invitation to contribute to a simpler paper to the Handbook of Geometry and Topology of Singularities. And what I showed you before was extracted from this paper, which will be soon on arXiv. And I want just to show you the abstract of our 2013 paper, because there we explain exactly what was our motivation. And there, in fact, what we can tropicalize is each time you have a ring and a map from a semi-group or a monoid to the ring modulo its invertible elements, then you can tropicalize any subset of the set of valuations of the ring using that map. And this gives a lot of flexibility, and we used only part of it there. But you see, seen like this, it looks very abstract. That's why yesterday and today I wanted to present a more graspable viewpoint. So finally, I will explain you exactly how splice-type singularities are defined. I give here an extract of the foundational paper of Neumann and Wahl, complex surface singularities with integral homology sphere links. So, splice-type singularities are defined starting from a splice diagram. And a splice diagram is a finite tree whose vertices are called either leaves, if they are of valency 1. Here you have 4 leaves, or nodes, the other ones. And here you have 2 nodes. And nodes have valency at least 3. We do not put nodes of valency 2. And the valency can be bigger than 3, and I will show you also an example of bigger valency. So we have weights on the edges, but near the vertices, and in fact near the nodes. So you see here, in the neighborhood of this node, we have 3 weights on these 3 vertices. And now we have several conditions to be imposed. First of all, these weights should be pairwise coprime around each node, which happens here with 2, 3, 7 or 2, 5, 11. Here you can notice that there are prime numbers, but they should not be prime. The fact that if you want to have small numbers, the easiest way to give an example where you have coprime things is with prime numbers. Otherwise, the numbers become rapidly big. Second condition, the weight on an edge ending in a leaf is bigger than 1. So here you do not see a weight 1, but it could be. For instance, here instead of 7, we could have 1, but not towards a leaf. And third, all edge determinants are positive. An edge determinant is something which is not a determinant, but whose formula is similar to that of a 2 by 2 determinant, AB minus CD. So here we fix an edge between 2 nodes. There is only one in this example. And we start with a product 7 times 11, 77. And then minus a product of the adjacent edges, all of them, those adjacent to this edge. So 2 times 3 times 2 times 5, 60. So we have 77 minus 60. This is strictly positive. This is a condition. Why? Because, in fact, the theorem here is that in this way we describe all links of isolated surface singularities which are integral homology spheres. And this is, in fact, a theorem of a book by Eisenbach and Neumann of the mid-80s. And this condition of positivity corresponds to the fact that the intersection matrix of a resolution of a surface singularity is negative definite. So that condition of negative definiteness translates in many inequalities, which in this realm of splice diagrams translates in these conditions about edge determinants. And here you see there is important thing. Here we are speaking about surface singularities in this theorem without any information about embeddings. So for instance, it's not known which ones correspond to surface singularities in C3. Which ones correspond to complete intersections? No idea. This is highly open. There are not even conjectures about that. What is happily known is that we know that all of them correspond to Gorenstein singularities, and this is due to a theorem I proved around 2010. So this can be realized by Gorenstein, but if you ask more than Gorenstein, for instance, complete intersections, then we don't know. And Neumann and Wahl discovered in this paper that they know that part of these splice diagrams can be obtained by complete intersections. And for this, they had to impose a supplementary condition, which they called the semi-group condition. So here, on the same example, which comes from their paper, I show what this means. So you see, the numbers are the same. The fact is that we have from this diagram to write a system of equations. One equation for each node. Please concentrate on the node here on the right, the orange one. To this orange one corresponds this orange equation here. I already explained that it's very easy to write what happens in the direction of a leaf immediately. So here we see the weight 5 in the direction of the leaf x cubed. That's why we write x cubed to the power 5. And the same x4 to the power 2 corresponds to these two. Now let's understand why we write here x1 to the power 1, x2 to the power 4, which corresponds to this direction towards these two variables. Here the rule is we have to look at this weight, 11, and now try to express it as a sum of the following numbers here, 3 and 2. What's the general rule? You take the geodesic which goes from the node, say, to the variable x1. It can be much longer. And you look along this geodesic and the nearby weights, which get out of it as hairs. So here you have only one, which is these 3. If you had more, you should make the product of all of them, like in the edge determinant condition. And now you get something in a product, so one number, associated to this geodesic. And then we have another number associated to this one. So here we get 2. So here the problem is, can we express 11 as a sum of 3s and of 2s? Which means, does 11 belong to the semi-group generated by 3 and 2? That's why it is called a semi-group condition. And here it's possible. You see that 11 is 1 times 3 plus 4 times 2. And these numbers, 1 and 3, we put them as exponents. You can have, and that's why, in fact, the splice diagram does not determine a unique way of writing a system, but then there is a theorem which says that different systems lead to equivalent singularities. So in fact, analytically isomorphic, but provided that we allow higher order terms. So that's why, in general, we have to add terms of higher order to show that we get exactly the same class of singularities if we change the representation. So in fact, there are a lot of subtle things here behind. But thank you for your remark. So you see why we put the 4 over x2, because x2 corresponds to this. We take the geodesic towards x2. Here the hair going out is 2, and we look at the multiplier of 2. So this is a way to associate those coefficients to the variables, and this gives you a monomial, and you put it there, and you write the equation. And all equations of a splice-type system are written in this way. And I think there is a lot to be understood about why doing things like this. For me, it's still a mystery in this rule, and one has to climb to another viewpoint which allows to do analogous things in other contexts. So for the moment, this rule, they found it cleverly one day, but it was as a flash, haha, we should do this. But what's really the meaning? In any case, their rule led to a wonderful class of singularities because it showed that a large part of splice diagrams, so integral homology spheres, can be realized by complete intersections. And this is analogous to what Briscorn did to show that exotic spheres, which lived only by cut and paste operations in the topological world, could be described by equations. So here we are inside a big dream to be able to write equations for the constructions of topologists. And this is still something for the 21st century. A lot of new ideas are to be invented to develop this, the way to make correspondence between equations and cut and paste objects. So here I pass rapidly. It's a slide only to show that if you have nodes of valency bigger than 3, like here, then to it corresponds, in fact, a Briscorn system. The monomials are the same in both of them, but you have to put coefficients, and here you have a rule. Each time you take a maximal minor of the matrix of coefficients here, it should be non-zero. So for people doing matroids, the matroids there should be uniform. And this is a condition to get an isolated complete intersection. So let's express precisely the Milnor fiber conjecture now. It states that each time you have a splice diagram which satisfies, moreover, the semi-group condition, and you choose an internal edge which joins two nodes, like here, let's call them A and B, just cut the diagram there and getting an A side subdiagram and a B side one. In this case, you see that you have the simplest possible ones which correspond to Briscorn complete intersections. Here, it's a hypersurface on the left because the valency is 3, and here is a surface in C4 because we need two equations. And now you see that by this cutting, one leaf gets represented by an arrow. As we said, leaves correspond to variables. The fact that it is an arrow tells that we have to cut the singularity by the hyperplane corresponding to z coordinate, z equals 0. So in this way, we get a surface inside the Milnor fibers of each singularity, a surface corresponding to this variable and a surface corresponding to this variable. Simply hyperplane sections, but not like in Lefschetz theorem where one looks for generic hyperplane sections. Here one has a preferred ones coming from toric geometry, intersections with a precise part of the toric boundary. And those are precise imported surfaces inside the Milnor fibers. So you see here it's something highly non-generic. It's toric geometry which dictates which special surfaces to consider inside. So the first, here what I wanted to say is that their precise conjecture tells that the Milnor fiber of this singularity above is obtained by splicing the Milnor fibers of these two singularities here along the surfaces obtained from the corresponding arrow variables. So now let us come to our strategy of proof. First of all, as I said, we are interested in the local tropicalization of the objects. For the proof, we need a smoothing of our singularity, so a three-dimensional germ, and we need to compute its local tropicalization. But it turns out that first we had to understand very well from the viewpoint of toric geometry and tropical geometry splice-type systems themselves. And what we proved is that, in fact, they are nice. The splice-type systems are Newton non-degenerate complete intersection systems. And from this viewpoint of Newton non-degeneracy, we get a toric geometrical proof of something Neumann and Wahl proved differently, of the fact that indeed they are isolated singularities and complete intersections. In fact, it's not at all obvious when you have a system to know why is it regular. Theoretically, there is a lot of blah blah, but when you have in front of you a concrete system, it's not obvious at all. And here, by looking torically, we can see this in a more general way, which we hope to be extendable to other classes. So how do we prove that they are Newton non-degenerate? Remember that this speaks about weight vectors. And I said that those weight vectors where there is something to check are precisely those in the local tropicalization. So we need first to find the local tropicalization. And this is very nice. We show that the local tropicalization of a splice-type singularity, so please look here, say corresponding to the same diagram I showed before, is as here. So it is, in fact, we are in four-dimensional space. So we have a four-dimensional regular cone. Let's look at a transversal section that, for instance, which joins the vertices of the coordinate vectors. We get a tetrahedron in our space, three-dimensional one. And now you can intersect the local tropicalization, which is a cone, with that tetrahedron. A basic fact is that local tropicalization of an object of dimension 2 is the support of a fan of dimension 2. So by that hyperplane section, you see a graph. And in fact, what you see, which is here, is in fact a tree which is isomorphic to the starting splice diagram. So this interprets splice diagrams which had been introduced by Ziebenmann in three-dimensional topology in 1980 inside the tropical world. You see, in fact, splice diagrams are intimately related with tropicalization. So the local tropicalization of those singularities is a cone on the corresponding splice diagram. And finally, we say, well, philosophically, it could not be different. But we proved it, and we also explain how simply from the toric geometry we can reconstruct the weights, which are here. And it's not obvious. They are not the simple toric weights we have there. There is something to be understood about the weights. And the mid drawing here is about the global tropicalization of the surface defined by those equations, if you don't look only near the origin, but everywhere at infinity. And it shows how the local tropicalization, which is this red part, embeds here in the global one. Yes? Can you? Yes? Always. The intersection of the local tropicalization, which is a cone, with a standard simplex, gives you the splice diagram. And in fact, it's embedded in a very nice way, which allows, in fact, there is convex geometry there, which is basic to all our computations which are done. We are guided by the convex geometry of this embedding. So what are the principles of our proof? In the overview paper, we detailed the proof in 28 steps, but really elementary steps. They seem, no? But you see, one has to combine local tropicalization, log geometry, and things like this. So let me tell less than 28. So first of all, we start from a splice diagram. We construct a special smoothing of it by adding suitable powers of a new variable, the deformation variable. Suitable because, again, there is the same problem, what to put as exponents. And we want to put exponents such that then the local tropicalization is adapted to the Milnor fiber conjecture. Okay. If we wanted to do something different, we should deform in another way. So now we determine the standard tropicalizing fan. Why? Because we saw how to deal in this context by the description for the surface singularities themselves. Third, we prove, knowing that fan, that again we have a Newton non-degenerate complete intersection. And in fact, the exponents, we choose them such that we arrive at Newton non-degenerate things. Fourth, now we take the strict transform. We know that it will be boundary transversal. And now we study our function f, which leads to Milnor fibers, using this modification of y. And what happens is that, in fact, it is good. It's not simple normal crossings, but it satisfies the hypothesis of a local triviality theorem of Nakayama and Ogos, which will be the last thing I will show in my mini course. So for the moment, again, please wait. But there is a nice theorem of Nakayama and Ogos which says that there we are happy in that toroidal context. Then we have to go and analyze the A and B side singularities. And there one has to be careful, not take a new system. One has to take A and B side systems which are carefully extracted from the first one, keeping some of the coefficients. This will lead at some moment to have isomorphisms of divisors in the log category, because we adapt. We cannot work independently there. And then, sorry? A and B are the two nodes, because the Milnor fiber conjecture speaks about you take an edge between A and B. So we have A side, B side. Now we relate the log special fibers of the three modified functions. Remember that the Milnor, a representative of the Milnor fibration, is obtained by rounding log special fibers. So that's why we have to look at log special fibers. So the diagram inside log geometry with which we analyze the situation is the same one. We have the special fiber here below, which goes to a point. But in fact, from the target disk and the ambient space here on the source, we get divisorial log structures which we can restrict to the two divisors, getting O dagger and Z of F composed with pi dagger. And then we round that. We round that logarithmic morphism, and this is a representative of the Milnor fiber. And you see that it is decomposed into pieces using the projection to the total transform of F. And everything was chosen such that that special fiber is combinatorially very connected to the splice diagram. And the relation is here, that in fact it decomposes like this, as the strict transform of X, and then the rest, exceptional divisor, comes out in three parts. This is done with many irreducible components, but now you can look at the dual complex of that. Here it's a configuration of surfaces in a 3 space. When you have surfaces cutting in a 3 space, you expect to have also triple intersections, so to get a dual complex of dimension 2. And in fact, here, not. They intersect really along a tree, which is the starting splice diagram. So in fact, you can cut inside the divisor following the edge AB. So there is one irreducible component there which corresponds to the edge AB, this one. And now if you look at the piece corresponding here in the total space of the Milnor fibration above this, and you look at its intersection with the Milnor fibers, we see the product structure predicted by the Neumann and Wahl conjecture, which is here. So the pre-image of this boundary AB of y tilde here inside, intersected with the Milnor fibers, is GA cross GB. And now we have to prove that what lies above these two other pieces corresponds to the cut Milnor fibers on the A side and B side. So on the A side and B side, we have to look at the analogous diagram. And what happens is there, in fact, the deformation is a little different, because for the starting singularity, we deform in a way adapted to that central edge. And on A and B sides, we deform in a way adapted to an arrow. So you see, each deformation, each smoothing is adapted to looking at a precise part inside. And this is what seems very interesting to us, is that when we want to deform, we have to think about parts of the exceptional divisors. And each part says, I want to be deformed in another way. And we don't have a general theoretical framework in which to think about this phenomenon. And I would be very interested if you know other instances of this, to learn why deformation is dictated by the internal structure. So the final thing is that we find inside the total transform of the function on the A side a divisor, and we construct an ambient toric morphism which sends it to the A part divisor, which is here. And those are isomorphic. So we have a concrete isomorphism induced by an ambient toric morphism, and that allows us to prove that, in fact, this isomorphism can be lifted to the log category. So at the end, we get here an arrow which lives in the logarithmic category above, and which gives, in fact, when rounded, the isomorphism of parts of the Milnor fibers. So you see that at no moment we go inside the Milnor fibers to do cut and paste. The isomorphisms are constructed at the level of logarithmic geometry. So this is the meaning of what I told, that one can avoid completely entering inside the Milnor fiber. We don't go there and look what happens. The concrete thing which is proved is a logarithmic isomorphism here. So I am approaching the end, and for the end I want to lead you to the definition of log structures, to give you a gradient flow which arrives at the definition. And the easiest gradient flow I know for the moment starts from a reinterpretation of a real-oriented blow-up of the center of the disk using polar coordinates. So let's see. When we teach polar coordinates at first year of university, in general what we write is a first system. X is r cos theta, y is r sin theta. And using complex numbers, we teach them that this can also be written as z is r times exponential of I theta. But you see that in all these formula appear transcendental functions: cosine, sine, exponential. And here we are in a context of algebraic geometry, and we would like to avoid as much as possible transcendental functions. So simply, we interpret exponential of I theta as simply a complex number of modulus 1. So we write simply that z is the absolute value of z times the sine of z. Why sine? Because if z was a real number, you would get there exactly the sine. And we teach students that complex numbers are in general not neither positive nor negative. But they have a sign which is corresponding complex number of modulus 1. So that's why this is a generalization of the usual notion of sign for real numbers. So we write simply that the sign is a quotient z over the absolute value of z. The same expression which allows to define the Milnor fibration on the spheres. So now we can look at those formulas in two inverse ways. The first one, which starts from C and which associates to C the pair modulus of z and the sine of z. The problem of this is that it's not defined at the origin. But if we look the inverse, we start from a point in r bigger or equal to 0 cross S1, Ru, we can multiply those always. That is always defined. And if you look at that map topologically, you see that this is a half line cross a circle, so it is an annulus with one boundary component, which is a circle. And that circle is sent by this map to the origin of C. So you get an algebraic model of the real-oriented blow-up. And moreover, an algebraic model which is rich as a structure, because if you look both at the left and at the right, you see that you have multiplicative monoids, which are not groups. What prohibits to be a group on the left is precisely the boundary circle, and on the right it's the origin. And that's why, for instance, in Gouloin's talk yesterday, he emphasized that monoids are crucial. And indeed, here, what is crucial for everything is that these are morphisms of monoids. And now, in fact, real-oriented blow-up can be interpreted using this map. So first of all, we will ask the following. If we do this, you see this modification of C is performed because we chose a special function on C, which is Z. Let's try to make it intrinsic, meaning we would like to perform this intrinsically on any Riemann surface at any point. We could do by choosing a local coordinate Z and doing this, and then verifying that it's independent of the local coordinate. But we want more. We don't want to choose. We want to arrive at a definition which, by its very nature, is independent of coordinates. So a way to do this is say, well, because everything happens at the origin, let's look at germs of holomorphic functions at the origin. And take a germ which is non-zero. Then it can be expressed. For the moment, we still have a preferred coordinate. We work with it, but having in mind that we want to remove it. So we write H as Zm times V. Now V does not vanish at the origin, so it is a unit. So if we want to find the sign, you see that the sign of H is exactly as above. It will be the sign of Z to the power m times the sign of V. And we want to extend this to the origin. There is no problem in defining the sign of V at the origin because V does not vanish at the origin. But the sign of Z is still not defined. Nevertheless, we know that if we lift this to the real-oriented blow-up, now the sign of V is defined at each point of the boundary, but it gets a different value at each point of the boundary. But you see that the previous relation shows you that once you defined the value of sign of Z at a point, you get a definition for the sign of H for all holomorphic functions. And now you can look at this map, which associates to the H the corresponding sign. Which H did we take? Those in the local ring without the origin. And this map, which associates the sign evaluated at a precise point of the boundary, is in fact a morphism of monoids, from the multiplicative monoid here on the left to the circle. Here on the right, you have a group. Moreover, you see that all such morphisms of monoids are different, and you get all possible morphisms of monoids which extend the usual sign if you look at functions which do not vanish at zero. So we know if it did not vanish at zero, we have the value. The problem is how to extend it. The extension is non-canonical. How many choices do we have? We have a circle of choices. Well, we replace that point by this circle of choices. This leads to the following construction on a Riemann surface. We have a point on the Riemann surface, and now we look at the sheaf of functions on the Riemann surface which are allowed to vanish only at the point. So the germs outside the point have to be non-zero, but at the point we cannot have the zero germ. And we look at this multiplicatively, so it's a sheaf of monoids. And now, how do we do the real-oriented blow-up? We look at pairs, a point of the Riemann surface, and U, which is a morphism from the corresponding stalk to the circle, which has the property that on units, it gives you the sign of the unit evaluated at the point, what I said before. And now we have a canonical projection to S, because XU, you project it to simply X. And we get this map of real-oriented blow-up, which is here. And now if you look at what we did, we can do absolutely the same, starting from any divisor D on a variety, normal crossings or not. We look at the sheaf of functions which do not vanish outside D, and then we round it by the same formula as before. And still more generally, if we look at what we got in fact not simply a sheaf, but a sheaf which was a subsheaf of the structure sheaf of the ambient manifold, what is written here. And the axiomatization of the notion of log structure is that in general you take a sheaf of monoids with a map to the structure sheaf. And what we ask is that we did not touch at the sheaf of units of the structure sheaf here. So this is not changed. This is a red condition. We want to have an isomorphism between the subsheaves of invertible elements on both sides. And this is a logarithmic structure. And here an important caveat is that you see in the example of a divisor, we get here an embedding, but in the definition we remove the condition to have an injection. Why? Because I explained to you yesterday that it's important to have flexibility to be able to restrict log structures. And if you restrict, in fact, this construction even to a divisor, well, you do not get any more injectivity. After restriction, you lose this. So if you want this flexibility, you are obliged to remove injectivity from the hypothesis defining your object. And in fact, if you look carefully at the restriction, you will discover that by simple restriction of sheaves, you lose the isomorphism you asked for. And then this needed a word which is called a prelog structure. And in fact, a prelog structure has an associated log structure, and one needs a lot of care to build the basis of the theory. And the basic paper in which this was carefully written is a paper of 1988 of Cueto called Logarithmic Structures of Fontaine-Illuzy. Illuzy told me that he was with Fontaine in the train towards Oberwolfach, and they had the idea in the train, and at Oberwolfach they met Cueto and they explained him his ideas, and he got enthusiastic, and then he wrote the foundational paper. But you see, his motivation was related with crystalline cohomology. So in particular, he was very far from complex geometry. That's why he needed things be written in the general framework of étale topology and things like this. So very rapidly, for those interested, you will see extracts from the foundational paper which defines rounding, as I explained you. That's why rounding is also called Kato-Nakayama space or Betti realization. I jump over this, and here at the end, I recall the way to study Milnor fibers using log geometry. And finally, I show the abstract of the paper of Nakayama and August, in which they prove the local triviality theorem, which works in the toroidal category. And in fact, their local triviality theorem works in a much more general context. So if you have other contexts in which you want to have local triviality, go there and see if their hypotheses work. Their hypotheses are written in a special log geometrical language, so perhaps you will need 1 week to understand really what those terms mean. For those interested, I have a list of references at the end on several themes I touched in this mini course about splice-type singularities, about uses of log geometry in the study of Milnor fibers, uses of local tropicalization. Again, everything magenta is clickable, so you get direct access to those papers. Uses of Acampos real-oriented blow-ups. So if you have some problems, you don't need to go to log geometry. You can simply use Acampos vision. For uses of rounding of log structures, you have other papers. And finally, here are some foundational books. For instance, Kempf, Knudsen, Mumford, Sandona was the first book about toric varieties and toroidal varieties. Loyenga is a very good reference for Milnor fibers in general, for smoothings. Eisenbad-Neumann was a book which presented the first time in a detailed way applications of splice diagrams to the study of singularities. Oka is a book about Newton non-degeneracy. McLagan-Sturmfeld, the first textbook on tropicalization, global one, and August, the first textbook of log geometry. So from this, you can then navigate according to your interests. I want to tell you that there will be a conference, a singular, tropical, and non-Archimedean interactions in Lille in June 2026. Please tell around you to people not to organize something else that week. And you can already get inscribed by clicking on the link below. And I hope to see a lot of you at that conference in Lille next time, and you see already here the speakers. And finally, if I am here, it's because I met at a crucial moment in my life when I needed dreams for doing mathematics. I met Bernard Tessier, and he always made me discover wonderful landscapes in mathematics. And it's still so each time I meet him, and for this, I don't know how to thank him. So I say thank you, but that means nothing compared to what I feel. So thank you very much, Bernard, and thank you very much to you all.